It's my pleasure to be standing here to talk, to move on from stars and to talk a little bit about exoplanets. I now lead a research group in exoplanets at UCL in London. But back in 2011, 13 years ago, I was a master's student at the KU Leuven. I was due to do my master thesis with Connie. But I also wanted to go on Erasmus. I wanted to go somewhere else, and so I asked Connie, is it possible to go somewhere while I still have to do my master thesis? And she said, yes, it is possible to go somewhere else if you go to this very specific place, Aarhus in Denmark, because I know someone over there. And then you can do your thesis there. Right? And then I asked, well, I don't know if she remembers this part. I asked, can I think about it? And she said, yeah, tell me tomorrow. And so I told her the day after that it was fine after I had looked up Aarhus on a map and I learned a few things about Denmark. And so I went to Denmark and I did my master project there with Jørn as well as with Hans, who's also here in the audience, right? And so in 2012, I published my very first paper about my master project, and then in 2014, a bit of a longer version of the same work, which I did together with Jørn and with Connie. And sorry, Douglas, I don't think we have a paper together quite yet, but there is always time. And so maybe we should do something about that. But this was about asteroseismology of exoplanet host stars. And I've gradually moved on a little bit from pure asteroseismology to host stars, but I have a warm heart for asteroseismology. In reverse, Jørn likes to talk about exoplanets. He famously sometimes calls them slimy rocks and asks why people should be studying them. But I know in his heart, Jørn's actually a big fan of exoplanets, as I am a big fan of asteroseismology, of course. So I want to take you to the exoplanets, and I want to use asteroseismology a little bit as a tool rather than as a method as such. And I think that's actually a testament to how far the field of asteroseismology has come, that it can just be used as this kind of tool to do lots of other science with, right? And as I begin, I want to talk to you a little bit about what we know about exoplanets. And so this is a graph where I'm showing you the solar system planets in white. So there's 8 white dots on this diagram here. You see the biggest ones like Jupiter, Neptune, and so on there. But if you look very carefully, you can see the smaller ones like the Earth to scale. Earth much smaller than Jupiter, of course. And everything else on this diagram is the extrasolar planets, the exoplanets that are around other stars. And so there's over 5,000 of them now, highlighting just how many we have to choose from. The number keeps changing. Many more planets keep being discovered all the time. And we can use those as laboratories. We can use those to try and understand how do planets form? How did the solar system form? How does the Earth fit into that picture? Are planets common in the universe? What kind of planets are there? And ultimately, what are their atmospheres like? And perhaps, do some of these planets have life, or are we alone, right? And so, to make the same graph a little bit more quantitative, this is showing you the mass of an exoplanet in Earth masses versus the semi-major axis. So that's the distance between a star and a planet. And if we put the solar system on the same diagram, then you see where they fall. It's a log-log scale. So solar system planets themselves are actually very diverse, right? They're very different from one another. Earth is right there at 1 astronomical unit and 1 Earth mass, as it should be. And if there's any fans in the room, there's always a few fans in the room. Pluto would fall off this diagram because it just doesn't quite fit on there, but I'm happy to put it on for you. Now, if we put the exoplanets up here, there's thousands of them, so they look something like this, right? And so you can see that they span a wide part of parameter space, some really close into their stars. In fact, many very close to their stars, interior to Mercury's orbit. Some far away, and lots of them in the middle as well. You might get worried that we don't have much right where Earth and Venus seem to be, but that's largely a detection problem, because if you really color code this graph by detection method, we find these planets in different ways. You can sort of see how each of these detection methods fills a part of that diagram, which is just highlighting this is an observational effect, really. We haven't completed this diagram yet. It's easier to find the top left part of this diagram, the massive close-in planets. We're pushing downwards, and so there's no real reason to believe we wouldn't eventually fill this part of the diagram as well, right? So different methods. I mostly want to talk a little bit about the transit method, which has been responsible for the majority of the currently known exoplanets. Right? So this is how a transit works. We look at the brightness of a star over time, and if we just do that long enough and at many stars enough, we will eventually get lucky, and a planet will cross in front of that star. And when that happens, that looks something like this, where a planet's crossing in front of the star. We can't see this top part, right? I want to be clear. We can't resolve stars. They're point sources, so we don't actually see this planet cross in front. But we see that total brightness change due to that planet. Planet's gone a few hours later, and the brightness returns back to 100%. And so this effect here, this transit, this small stellar eclipse, if you want, is the transit, and that's how we infer there is a planet, right? And so this works really well, and we found thousands of planets in this way. Now, how would we do that in practice? We would need to look at lots of stars for quite a while, right? And we do that by using telescopes such as the ones that have been mentioned today, like Kepler, and we look at the brightness of many stars over quite a while, and then you measure this change in brightness, this change in flux here, right? But immediately see how important it is to understand something about stars here, because we don't see the star and we can't resolve it, but if we knew what the star was like, let's say we knew it was the size of the sun, then we could now infer what the planet was like, right? We could put the planet up here. Because of the size of the dip, we would know how big that planet is here as a result, right? And so this might be an Earth-sized planet. This is not to scale. An Earth planet would look a little smaller. But if we observe the same exact effect, the exact same transit, but we didn't know the star was like the sun, perhaps we thought it was a little bigger, something like this, 20% larger, then we could get the same effect if we just had a bigger planet, right? And so that planet would be a little bigger. Maybe it's a little bit more like Neptune, a bit bigger than the Earth somewhere, right? And so this is telling us right away that if we don't know the size of a star, we don't know the size of the planet. And so it's really key to be able to get planet size. To get planet size, we really need to get these stellar sizes quite right. Okay, so here there are many ways of doing this, but the gold standard and by far the best way of doing this happens to be asteroseismology. It can deliver us this sort of very precise percentage level stellar radii in some cases. To do that, we usually need to go to space. We need to get photometric data over time that is precise enough. So this is space for you. And I plot up the Kepler field here because I think it's always nice to see where the Kepler field is. It's right in the summer triangle between Vega, Deneb, and Altair. If you look at the sky in summer, these are 3 stars that are very easy to find. And that's the region where the Kepler field is. This is where we know the most exoplanets in the sky currently today. So if you look up this summer, that's where you can look at. And we have other telescopes like TESS and in the future Plato that will do similar strategies to find more planets. Right. Okay, so it's some kind of beautiful synergy here in that asteroseismology isn't just important to be able to do exoplanet science, but we can actually use the same kind of data to do both of these things as well. And that, that's a very nice kind of coincidence almost, and very nice synergy, but it's of course there because stars change brightness over time due to the oscillations, right? As the star changes temperature and changes size due to the oscillations, its brightness changes, and that is giving us the oscillation patterns we can study. And so this is an example of Kepler. This is 20 days of Kepler data. The real data set is actually 4 years, but I'm just showing you 20 days. And you see kind of wobbles of the star, and then you see in highlighted in blue the 2 transits here, so a 17-day period planet transiting twice. And then in between, the orange bit might just look a little bit like noise, but it's actually a pattern of oscillations, right? And it's hard to see exactly what's going on here, because in time, it's quite hard to see the structure, because stars oscillate with multiple frequencies at the same time. But if we take a Fourier transform of this time series and we go to frequency space, we can see that this is not just noise. There's actually a pattern to this, right? And so in this case, this is what the pattern looks like. It's really nice, actually. It's very clear in this case. This is Kepler 410. And from this pattern where you can sort of see the frequencies, the regular spacings, the delta news and the new maxes, as the astroseismologists like to call it, and then the individual frequencies, we can model this star really well. In this case, it's about 35% larger than the sun. And we can do that to this 1 to 2% precision, so really good, which can then translate into that precision of the planet. Right. Now, there's more to that. And if you would zoom in on a little bit of this, you would be able to see that actually these individual frequencies furthermore split into triplets here, right? So this is just a very small part of that frequency range. And you can see there the L equals 1 mode on the left. that splits very nicely into that triplet with the m-1, 0, and 1. And this is the rotational splitting effect that I think Saskia explained so nicely earlier, where you sort of see that because the star's rotating, some of these frequencies are shifted a bit higher and others a bit lower. And so this tells us something about the rotation rate of this star. But it does something more than that. It actually tells us something about the inclination angle of that star relative to our line of sight because of cancellation effects as an observer. And so from this pattern here, and we see this for all the frequencies, not just for this one, we can actually determine the spin angle of that star relative to our line of sight. And as an exoplanet scientist, that's really interesting because we already know there's a planet there. We already know the orbit of that planet. And so now we can compare that to the spin of the star to see if they're aligned or misaligned. And in many cases, we found stars are misaligned from their planetary orbits. And that tells us things about the formation, how stars and disks might have been aligned or misaligned, how planets might have migrated or become misaligned over time, and so on. And this idea is applied to not just solar-like stars, which I'm showing you a very nice example of, but we can do this, of course, to some degree for other stars as well. There's a very nice paper by Constanze Swintz on Beta Pictoris, one of the most famous exoplanet systems, which is a hot star, an A star, where this is harder to do, but you can still get some of these rotation and inclination effects out of there for the fast-rotating stars. So I think a bright future also for hot star asteroseismology there in exoplanet science. And then, of course, the last part here is we model an exoplanet transit, and here you can see the real example here to scale. So I've normalized the flux to 1, and then you see that dip going down to 0.9997 or so. So you see that the actual transit is only 300 parts in a million, kind of highlighting why we need this space data, this really precise data to do this, to get this stellar effect so nicely. And then we can put all of this together, and we can now see the system as well. And this is now this is to scale an example of the system. This is the star with its 17-day orbit planet to scale. You see here how big it is relative to the star. It's quite small relative to a real star, right? And you see sort of the inclination angle we've inferred as well from the rotation of that star, right? And this is just one example. This has been done for many others. Just want to show you a recent one where we were working on. This is a test system. This is New Tulupi. This is a really interesting star as well. This is a naked eye star in the Wolf constellation. So it's also one you can go look at if you're interested. We already know of 3 planets there. And same thing there. I'm showing you just 2 transits here highlighted. I can't show them all. They don't fit into the same diagram. But again, in between, what might look like noise is really stellar variability. You can take a Fourier spectrum, and then we can look at the frequencies. You see the full frequency range there on the left. And so you see this kind of range. And then with the dotted lines is highlighted a small frequency bump, right? And this is much harder to see now. And the zoom in here on the right. And so now you might become a bit more skeptical, but really we can actually extract frequencies here. Some people like Hans would do it by eye, others would use some other methods, but it can definitely be done here. And it's quite convincing actually to do this, right? And so this really works in many cases, right? And this is then the planets, and again, we put those things together and get information on the system. This is how it looked like in the ESA press picture here, sort of Wolf constellation. 3 planets in a 10-day, 27, and 100-day orbit. So really nice, different kinds of planets that we can then study in a lot more detail thanks to asteroseismology. Now, that's all good and well, but I want to take you to a little bit of a more general explanation as well, not just looking at any one specific system, but looking at a sample of systems, looking at populations of exoplanets. What can we learn beyond just getting very precise properties for any one planet, right? And so here again, asteroseismology can really quite shine because there's many ways of getting stellar properties right. In the early Kepler days, this was quite hard. We typically had a 20–25% uncertainty on the radius of a star. This has improved most of the time now with Gaia, with spectroscopy, and so on. We do better than 10% for most stars that we're interested in. But with seismology, we can get this really tiny precision level, right? And I'm showing you here what that means visually, right? If we don't know the star to better than 20%, we'll never know the planet to better than 20%, and that dotted line planet might be 20% larger or smaller, and so you can see quite how different that is compared to the 2% uncertainty effect, right? And this has real implications on stuff that we can just simply not do if we don't reach the needed precision, right? This is an example of the population of exoplanets from Kepler as it looked like in the early Kepler days, right? And this is just planets from 1 to 100 days, so about up to Mercury's orbit. From 1 to 4 Earth radii, so I'm only showing you the Earths and the Neptunes. I'm cutting out the Jupiters here. And if we look at those, well, we don't see very much. This looks a little bit like there's planets everywhere, right? There's not that much structure to this diagram. But as the stellar parameters improved, and therefore the planet parameters improved, more structures started becoming apparent. And this is a version without seismology still, where you can start seeing, perhaps if you have good eyes, that around 2 Earth radius, there seems to be fewer planets there, right? You might be skeptical, it depends on who you are. Hans would probably believe me right away. But there is fewer planets here around 2 Earth radii, right? There's a bit of an underdensity in that region. Right? And that's because we've now improved the uncertainties. But we still have that sort of 10% error bar here. This is about 1,000 data points on this diagram, but for about 100 of them, we were able to do asteroseismology. And then we can overplot those on this same diagram. We will shrink their uncertainties to about 1 or 2%, and then they look something like this, right? And now you probably do believe me that there do seem to be very few planets in that 2 Earth radius regime, right? This really seems to be like this population splits into 2. It splits into this higher, larger region around 3 Earth radius, and maybe another blob around 1.5 Earth radius, right? And if I'm showing you this in a just only the seismology data points, this is how it looks like. This is the seismology data points, the same data points from the previous plots, with a line fitted through that valley as we now see it. It has an orbital period dependence, and it splits what we now believe, or what we now typically refer to as the super-Earths and the sub-Neptunes, right? And I'm only telling you the observational story, but there's really a whole theoretical story behind this as well. And in fact, this radius valley had been predicted even before it was observed. Back in 2013, various theory groups suggested that because lots of these planets are so close to their star, right, they're all closer than Mercury is to the sun, they would receive lots of X-ray and UV flux, and that would influence their atmospheres, causing some of them to lose their atmospheres due to photoevaporation. And that effect would strip some of the Neptunes of their atmospheres, turn the Neptunes that are larger with hydrogen-helium atmospheres on top into just Earths that just have a core of iron, magnesium, and silicon. Right? And it would change their size and kind of cause this bimodal distribution. And because it's so hard to hold on to a tiny atmosphere in the middle, we would then get this kind of valley in between. So this had been predicted, and in fact, the theory predicted where this valley would be, around which size it would be, and it predicted there would be an orbital period dependence for that valley as well, which is exactly what has been observed. And this is something that nowadays has been replicated in many different studies, with and without asteroseismology, and it's become very much the standard paradigm, I think, for how we interpret small planet properties. We now know that they really do come into these flavors in many ways. And there's lots more research going on this topic of the radius valley. I just want to show you a quick one here, which is just worked by my PhD student, Cynthia Ho. She's going to be my first PhD student to graduate. Unlike Connie, I don't have 40 yet. But this is going to be my first PhD student to graduate in a few weeks' time. So she looked at this radius valley and showed very nicely that it's not just this line, it's actually a plane if you look at not just period and radius, but period, radius, and stellar mass. And again, this is expected because it depends on this X-ray and UV flux, and of course, with different types of stars, you get different levels of this flux. And so you can see how that there's kind of a plane separating the Neptunes and the Earth in period, stellar mass, and then planet radius space. All right. Okay, great. For the last little bit of my talk, I just want to make sure you don't come away thinking that the only thing that we care about is planet radius or stellar radius. We do actually care about lots of other types of parameters as well. And so one thing I want to highlight here is that we also want to understand planet compositions, right? I made this point, we need to know the size of the star to know the size of the planets. And if they're both bigger, then we might be wrong about the planet size. That's true. But very much the same applies to, for example, planet masses and stellar masses, right? We typically measure a planet mass through the radial velocity method, where we look at the star, we look at its wobble, we look at its redshift, at its radial motion, which causes a redshift or a blue shift in the star as a planet orbits around the star, but actually star and planet orbit around their joint center of mass, right? And so we don't see the planet in this case, or in either case really, but we do see that star wobble, that star red and blue shift, and we can observe that, right? And this gives us an idea of planet mass, but we again need to know the stellar mass to do this, because this is a gravitational effect, right? And so again, if we got the stellar mass wrong, we would get the planet mass wrong, right? So this is a very basic level. Similar properties apply here. We need to know stellar masses just as much as planet masses, as the stellar radii, right? And so the picture we want to then build up is something like this. We want to understand star masses and stellar radii. From radial velocities, we can then get planet masses. From transits, we can then get planet radii. We then combine those two ingredients to get densities of the planets, and those densities can then be linked to compositions where, for example, dense planets will be very rocky, low dense planets will be gaseous or water-rich or ice-rich or so on. Right? And then the final step we really want to take here is we want to somehow link these compositions back to some kind of explanation as to why planets are different. How dense are these super-Earths or are these Neptunes that we're looking at? Why are they in a certain way? What is their composition? And does that link somehow back to the stellar properties? And in particular, I think something quite exciting is trying to understand whether this may link back to the age of these stars. Right? And ages are hard, but seismologists always promise they can do it. And so this is something that's very interesting. Now, you might wonder, why do we think there might be a link to age? But let me just give you one example of why there might be a link. Right? The galaxy has changed a lot over time. Right? And if you look at older stars, they have relatively little iron available, more magnesium and silicon relative to iron, more alpha over iron as galactic evolution people would call it. But that stars forming more recently have a higher iron ratio relative to magnesium and silicon. These are the elements that make up the core and the mantle of planets like the Earth. So perhaps these planets are different depending on when they have formed, when the stars have formed, when the planets have formed. Right? And so we can then look at a sample of systems here, like this is a mass radius diagram. So this is planet mass versus planet radius, and then some composition tracks, right? So if you had a pure iron, nothing else than iron, we would have that certain track between mass and radius. If we instead mix it up with some rock, some magnesium silicon rock, then of course it's less dense. So for the same mass, you get a bigger planet, right? And then we can put the planets on this diagram, and they look something like this. They kind of span this regime, right? And I'm only plotting the planets here that are actually rocky. I'm ignoring the Neptunes that are having this hydrogen helium because they're harder to interpret. Right? And now we can link that to their age, and we carefully derived ages with Gaia and with other parameters, with seismology when we could, but we don't have seismology for all of them yet. But nevertheless, there's something quite intriguing happening here, which is if you look at this versus age, you might start seeing that the upper line there has the yellowest data points, the oldest stars, and perhaps that's suggesting that those planets which have more magnesium silicon and less iron are indeed those that are oldest, 10, 12, 13 gigayears old, and those planets that are more like 2, 3, 4 gigayears old seem to have this higher iron content. So perhaps there is something to this, and we would really look forward to getting better ages from the seismologists over time. Fortunately, that's something that's very much into the future, I think. We're very much looking forward to Plato. And I like to show this because it really highlights what I talked about today. Plato is, of course, an ESA mission that will launch in 2026, or end of 2026. And it really has this dual purpose of exactly what I was just talking about today. It wants to do asteroseismology, and it wants to find exoplanets and combine those two things to do very intriguing things. I like the last bit there, including its age, which has been the promise that has been made to us exoplanet people, that this will be something that we can do, and so we can get these bigger samples better studied than we have been able to do in the past. Because here you're showing you the Plato fields relative to, for example, the pink there, which is the Kepler field. And you see just how much bigger the Plato field is, enabling so much more scientific opportunities than we might have had with Kepler and its relatively small field of view. Right. So with that, I just want to end here. I think I've made the point that asteroseismology has been key to understand exoplanets. It's really been an excellent tool to help us understand exoplanets and their properties in individual systems, but also for ensembles, for populations, and so on. We've done that lots of it with Kepler and TESS. With Plato, we're hoping to do even more. And if people ask what's the most interesting discovery so far in exoplanet science, we think they're ahead of us. So perhaps the most exciting discoveries are the ones that are yet to come. With that, thank you very much.